Okay, so we're at the section 32 now, the notes, visual approach to integration. We're going to be computing what's called assigned area. We will certainly give you pictures. We will do the pictures, and we'll try to indicate to you what we're looking for you to do as well when you're given these pictures over here. So this one over here, I'll read it to you. We'll get to the whiteboard later. I'll read this to you, and I'll talk about this object over here, about how to do that integration and how to write the number -5. Typically, we give you problems that represent what we're trying to teach. And by that, you're going to be able to reinforce this with similar problems to make sure that you understand what we're teaching is what you need to know. Okay, so next thing up, we're going to talk about Riemann sums. I realize when you're reading through this stuff over here, you might say, I have no idea what I'm talking, what I'm reading. We got to go through examples, by the way. And so I'll talk about simple examples, but I do try to provide visuals for you to help reinforce what the words are saying. All right. What words are we talking about? The words are on this piece of paper over here. We will read this to you. We will go through the picture and explain how this stuff here relates to the picture with the intent that we want you to be able to do problems. We will do more problems, of course, at the whiteboard, but you know what the goals are. Our goals are to get you guys to do homework. You got to start working towards that goal. Is it difficult? Of course it is. Education in general is difficult. It takes a tremendous effort to become educated. What I mean by that, it's not the effort that I make, it's the effort that you make is going to make all the difference in the world. So I'm going to go to the whiteboard and, stop yammering on about this stuff over here. And I'm going to go to the whiteboard and I'm going to share my whiteboard with you and we'll talk through it. All right, so after all that conversation about Riemann sums, I got to get my whiteboard working again, sorry. So all that conversation about, Riemann sums and doing examples, I hope you start to appreciate that really what we're doing is we're doing rectangles, and those rectangles above the x-axis, right, would have positive heights, and the ones below the x-axis would have negative heights. So I'm going to say this over here, and we'll go to storytelling later. Looking at this shaded region over here, this shaded region here would be represented by a positive number. Well, let's talk about the area of it first. This could be positive. And this one over here, again, remember when we did the Riemann sums that these things have negative heights over here. All right, definitely negative heights. The S all evaluate the negative numbers. This would be negative. I could call this area 1. That's a nice object, right? What is it going to be? 1/2. What's the base of that? 2. And by the way, I'm looking at the picture. By the way, the picture could be wrong. 4 would be the height of that. What does that give you? Area 4. Let's do the area of this. I'll call it area 2. Notice I'm calling it area now, not signed area. I'm just calling it area. 1/2. The base appears to be 3. And the height of that, I'm just looking at a physical object now, looks about 6 to me. And what's that going to give me? 9. Now, some of you say, oh, it's 4 plus 9 is 13. No, this is negative area in the bottom. This is positive area. So what's it going to be? It's going to be 4. That's the area above, plus the area below, which is actually -9. That will give me -5. So I'm going to see it over there. Now, something to say is, okay, what if you didn't give me the picture? Could I have done that? Well, what I want to do is I want to visualize what they just said. They said graph f of x equals 2x. I'm going to visualize now. That to me looks like this over here. I just graphed this and shade the region between the x-axis and f of x from x equals -3 up to x equals 2. So again, I'm just reading now. They said graph that line and shade the region between the x-axis and the function f from -3 to 2. I'm going to do my shading in now. Again, I'm just reading now. I'm going to put my points down too, okay? Let's just point over here. -3, -6, and this point over here is going to be 2, 4. Again, I would be able to, read and get that. And then they say, show that the total signed area is -5. Well, I think we did this before. If you recall, I said the area of this thing was 4, and the area of this thing over here was, what did I say it was? 9. Area above the x-axis is positive. Area below the x-axis is negative. So what do you get? 4 plus -9, which is -5. They asked me to do that. Here they also said that it can be represented by this statement over here. All right. So this is important. You're seeing a connection between these symbols, which we know is very difficult to do by doing a Riemann sum, is -5. Right. We know that now. All right. Let's go to the next thing up, which are these Riemann sums. We've done Riemann sums for a while now. Now they're going to say there's going to be Riemann sums where the partitions may or may not be equal size. So I'm going to read this to you, and I got to be honest with you, this confuses a tremendous number of students. We are not trying to confuse you. We will go to an example and we will explain what these letters mean in the example. But right now, what do they give me? And I'll read this to you very carefully. These are Riemann sums. Have we done Riemann sums? Yes, we have. What does it say? Riemann sum denoted by, well, that R stands for Riemann. Then they got F, they got P, and they got C. They say the Riemann sum denoted by this for the interval between A and B is defined by choosing a partition P. So now I know P is a partition. We'll talk about this with a concrete example. That starts at A and goes up to B, where they start giving me points along the way. They're not saying they're equally spaced, though. All they're saying is the very first point is x0. The very last point is xn. Then there's a bunch of points in the middle, x1, x2, all the way up to xn minus 1. Right? Then they go on to say there's sample point C. That's going to be given to you as a set of numbers. The set of numbers, the CIs, are going to be on these subintervals. For example, C1 would be on this first subinterval. C2 would be on the second interval, so forth and so on. How do I know that? I'm looking at this right over here. All right. We certainly know what the delta x is in the problem. It's going to be the length of the interval, right? Upper minus lower. So then they claim over here, it's basically to get the area of the Riemann sum, you're doing this business over here. Now, granted, in a lot of schools, they drop it at that and they say, okay, you go do problems now. All right. They told you what a Riemann sum is, go do problems. I mean, it's probably not a good idea. What I want to do is I want to talk about this relationship to the integral. And the relationship of the integral says this. It says that if the partition starts to go towards 0, that this thing over here, which we did in the past, will be the same thing as the integration. We did that already. What do? Equal partitions, and we let n go to infinity, which meant the partition went to 0. Let's take a concrete example of a problem. Calculate the Riemann sum for this. Now, by the way, they are telling you what Riemann sum want. They're not saying R6, L6, M6. They're not saying as n goes to infinity. They're telling you this. F of x is equal to x. I'm going to draw a picture of that right here. Yeah, I'm tracing over my picture. What's this thing over here? This line here is f of x. Then they say the partition starts at 1. That's 1. Then it goes to 1.2. This is 1.2. Then it goes to 1.5. Put that down for you. And then it goes to 2. I'll bet I go too fast with that. We just put the partition down. Then what did they say? They said C1 is the sample point between 1 and 1.2. And what is it? They chose 1.1. That's a sample point. Now they took a sample point between 1.2 and 1.5, and they said 1.4. Yeah. Then they took a sample point between 1.5 and 2, and what they say? It's 1.9. Now what are they going to do? They're going to take the area of each one of these rectangles and add together. Let's do it. All right, how many rectangles are there? 1, 2, 3. Let's write it down. The Riemann sum for this over here, well, let's take a look at it. What's the base of that rectangle? 1.2 minus 1. I'll write that down for you. Times the height of that rectangle. Well, the height of a rectangle is going to be f at 1.1. I'll write that down for you. We'll do the computation later. Plus, what's the base of the next rectangle? It's going to be 1.5 minus 1.2. What's the height of that rectangle? Well, the height of it's going to be the function evaluated at 1.4 plus, what's this guy's base? It's 2 minus 1.5. I will do the computations later. F of, what are they evaluating the function at for that? F of 1.9. It's not that bad. So what do you get? I hope you know f of x is equal to x, by the way. Is that right? Yeah, it is. What's 1.2 minus 1.2? What's f of 1.1? 1.1. What's 1.5 minus 1.2? 0.3. What's f of 1.4? It's 1.4. What's 2 minus 1.5? It's just simply 0.5. What's f of 1.9? It's just 1.9. Someone could say, do I need to do the arithmetic? Yes, you do. And I'm going to do it for you. 2/10 times 11/10. 3/10 times 14/10. 5/10 times 19/10. Common denominator, 100. 22 plus, let's see, 30, 42. And 5 times 19 is 50 and 45, 95. Oh yeah, I make mistakes sometimes. Let's see, did I make a mistake somewhere? 22 and 42, 64, 64 and 159. I can write it as a decimal. And what are you going to get? What would you get? 1.59. Done. All right. Let's talk about the other thing I'll do. Sketch the graph and geometrically compute what happens if the partition goes to 0. Well, you know what? The graph is already here. So what I'm going to do, if the partition goes to 0, it's going to fill up this space completely. All right, fill it up completely. So I want to point out what I'm looking at. I'm looking at an object that looks like this over here. And I know that object. I've seen it before. So it goes from 1 to 2. What's this point over here? Well, this is going to be 1, 1. What's this point over here? 2, 1. What's this point over here? Well, that's going to be what? 2, 2, right? All right, let's do it. I want to do this little tiny guy here. And what's the area of this thing over here? Let's see, 1 to 2 is 1. And 1 and 0 to, well, just 1. What's this guy? Let's take a look. 1/2. What's the base of that? 1 unit. What's the height of that? 1 unit. What's that going to be? 1/2. What's a half and 1? 3/2. So what are we saying? If we were to integrate this guy, doing a complete Riemann sum for that guy, and we started at 1 and went to 2, x dx, and we did that partition size going to 0, we would get 3/2, which is what? 1.5. All right. Now, someone could say, well, you know what? This is an overestimate. And, kind of looking at it, it kind of makes sense that it's an overestimate looking at the picture. All right. Not bad. So here's the deal. We're kind of done with the introduction. We need to go to the examples now. We'll go through the examples. We'll do some problems as asked for. Of course, some of these are going to be really simple to do if you've been following along, and some are going to be more difficult to do, depending. I will say this with practice, though, everyone gets good at this. Thank you for paying attention.